10 a.m. French time, European time, 3 a.m. in Minneapolis, 6 p.m. in Korea. I hope we have people from all over the world. We will wait for a few seconds for everyone to slowly connect and solve whatever connection issue they have. We are very happy to be here at the end of the year, the last webinar of the year. And I have actually the chance to not be alone today to discuss microprocessing challenges and how we can tackle them using beam shaping. Actually, it's a presentation that I have made for the first time at the UKP workshop earlier this year. And I made it also twice additional times in Clio and in Dresden. And actually, people really think generally that it's pretty useful because it's giving a big overview of what we can do. And last time when I was in Dresden 3 weeks ago, actually Eric attended that conference and apparently was frustrated by the number of questions he was having. So I gave him the chance to ask all these questions today because I believe probably Eric's questions are the same questions as everyone. So welcome Eric on board for that webinar. Yeah, can you?
Yeah, hello.
Okay, great. Maybe you want to quickly introduce yourself?
Yes, my name is Eric Rowley. I'm a principal project lead at Boston Scientific. I specialize in multi-axis motion and multi-axis precession with femtosecond lasers. We manufacture micro-medical devices for surgeons. So
okay,
much of the work and much of the things that you're presenting are directly applicable to my work as well.
So you remember that at the end you can join our sales team, Eric, if you want to buy our system. They are connected as well. Huh?
Yes.
Yeah. Okay. So actually, let's start. I want to let you know that so Eric will be asking a lot of questions during the webinar. We will make stops so that he can ask his question. But you can also ask all your questions. There is a Q&A mode on the right bottom of your screen. You can write all the questions. And in the end of the webinar, we will take some time to review your questions and hopefully answer all of them. So the agenda today is the following. We will be quickly presenting Cailabs. We will be also quickly presenting the different challenges of microprocessing. And then we will actually go through a lot of different process results that we have had over the 3-4 last years at Cailabs on microprocessing. So let's start with Cailabs in a few words. Well, Cailabs is actually a French company, if you have not guessed from my accent already, who is doing beam shaping. So we actually shape laser light for different applications. And all that is actually initially based on MPLC, multiplane light conversion. It's a unique way to shape light, which was invented in a lab in France something like 12 years ago. And the company is now 10 years old. And along the year, we developed the product to answer challenges in different applications. You can see our different product line on that slide. The three in the middle product lines are actually telecommunication. We come from telecommunication. The one on the right is mostly defense application, but I am working for Canada, the product line on the left, which is made for laser processing. So all the parts in the world which are manufactured using a laser, at Cailabs, we want to improve that one step of the process, which is using a laser. That can be using CW laser or femtosecond or actually pulse laser in general. So as I said, the company is 10 years old. We are now more than 90, and we have actually raised 43 million euros over the last years to develop the technology. So this is where we are in France, in the west of France, and this is our brand new building that we are very happy of, with actually the only optical ground station owned by a private company in Europe. But that is not linked to laser processing. Nonetheless, it's pretty cool. And one more time, we are actually developing, manufacturing those systems here in Rennes, in France. And obviously, the objective is then to sell them. So let's go to the technical part now. Challenges of microprocessing. Well, actually, microprocessing has really been revolutionizing a lot of industrial application over the years. From electronic to flat screen to semiconductors mainly, but there are also applications in medical and all that. But still, everybody is actually really looking at further scaling up microprocessing, and challenges must be overcome for that scaling up. I like actually that machine on the left because it's actually beautiful. It's big and at the same time full of R&D and at the same time super industrial. It was actually developed by Lazia. It's using a kilowatt femtosecond laser from amplitude, and currently it's being used at the IIT. So we are not all in that project, but I love the machine, and I think it's a good example of the R&D which is being done currently, because they are looking at really scaling up the processes using a lot of power and using some R&D beam shaping system. So the project is multiplex. It's ending, but I think they are still developing the process in Aachen. So it's a good opportunity to tell you that there is a good conference in April. For those who don't know, I guess all of you know, but for those who don't know, there is actually an excellent trade show and conference in April in Aachen. I will have the chance actually to present some results on welding over there. I actually strongly advise to go there. It's called AKL, and very probably the visit of the lab will be amazing, as it is every time, and you will have the chance to see that beautiful machine very probably. That machine is addressing the challenges of microprocessing. What are they? The main challenge, which is generally pretty classical in the industry, is to increase the yield. Microprocessing machines are a bit expensive, and you need to always manufacture more and more parts per year to improve your return on investment on this machine. This means increasing the yield and increasing the process speed. How to do that? There are many ways. In the past, mainly the focus was on increasing the laser power and the scanning speed of the machine and of the process. But we are reaching limits, because currently, if you have more power, you will actually, if you just simply use it, you will actually just damage the part, and it's not going to work, and you're not going to go faster. So you have to use smartly that energy, which means two things mainly: parallel processing, so having multiple beams and doing either multiple parts in parallel, either actually on the same part, drilling, for example, multiple holes at the same time. It's also possible using smartly the energy by shaping it. So we will be discussing those 2 points: parallel processing and optimally shape the light. Another challenge, which has always been a challenge for microprocessing, is increasing the precision. Actually, it is somehow the DNA of microprocessing is to look at super low precision, super small parts, super precise parts. There are many ways also to do that. I would say that 2 classical ways, which are pretty well studied for years, is increasing the numerical aperture of the setup. We are reaching limits on that point, and lowering the wavelengths. Everybody is looking at lowering the wavelengths from IR to green to UV to deep UV. And this is working, but again, there are other ways to go to lower scale. You can be using diffraction-free beams like vessel beams, or optimally shaping the light. Again, we will be discussing those 2 points today. One last point, which I believe is really potentially huge, is fibering. For now, all those femtosecond lasers are free space output, which means that you have to put them somehow on an optical table, and the application with fiber laser are still pretty much R&D. They are not really industrial yet. The day a femtosecond laser can be put on a robot arm and you can actually use it, just moving the robot arm around, for example, a plane, you will really open new application, and that's probably a big scaling up of microprocessing. The big challenge is that you have to find a fiber which is propagating that femtosecond beam. Generally, it's a hollow fiber, and those fibers are actually complicated to inject and are extremely sensitive. So the big challenge is to stabilize the beam before injecting it. There are 2 main ways to do that. One is active, one is passive. The passive solution is based on multiply line conversion, and we'll be discussing that one as well later on. So here we are for the challenges that we will be discussing. Just a quick word to say that at Cailabs we have standard solution to address these challenges, but our strength is also to develop customized solution to each specific need. So if you have the chance to discuss with Thibaut and Alex, our business development team, you should not hesitate to give them your craziest wishes, and we will see what we can do. But our strength and our DNA at Cailabs is to develop custom solution. I don't want to spend too much time on setup. Setup are super important, but they are generally pretty similar, not exactly similar, but pretty similar. So I will do it once and for all. This is a typical setup. with a laser. This one is orange, but we work with the lasers of all colors, the blue one, the gray one, the black one. No problem on that. We are compatible with all those lasers. Generally, for now, we try to develop, to use our off-the-shelf product, Canada Pulse, and either you adapt the product to the environment, either you adapt the environment to the product. Because we want to use a fixed product, we have to adapt the environment, which means adjusting the beam to the input beam of the Canon Pulse. This is being done using, for example, a beam expander to generally reduce the size. But this is not a must, and if your need is to have an input which is directly bigger, it's also possible. Then there is 1, 2, 3 lenses. In that drawing, there is just one, but can be more. Most of the time, there is periscope, and it's going through a scanner and left data. We are also compatible with micropulse objective if needed, and some of the results are actually with microscope objectives. So this is it for the presentation of the challenges and the application. Now we will reach the funny part of the presentation, the process results, and we will start by focusing on how to improve process speed. I want to make everybody work a little bit because it's a good way to wake you up for the Americans, keep you awake for the Asian, and for the European, I would say just maybe waking you up somehow as well. So we will be looking at some survey, and give me a second. You should now see on your screen a survey which is related to process speed. So for surface texturing, which is said to be the application of the future for microprocessing, what should be the target in terms of speed increase compared to the current state of the art to really expand the market? This is just asking you your opinion, so you for sure have an opinion. Do you believe it's multiplied by 2, by 10, by 50, by 250, by 1,000? Of course, there is not a single answer on that question. So I will give you like 30 seconds to vote. So take your time, but not too much. And give me your opinion. What would be your target in your mind if you want to really scale up surface texturing and reach big applications? So what are the big applications for surface texturing? I see 2 of them, at least there are 2 of them which I really like. One is texturing the wings of the airplane. Why would we do that? We all know that there is a big challenge on actually reducing our carbon footprint, everybody's carbon footprint, and reducing the consumption of aircraft is super important. And actually, by drilling small holes in the front part of the wing, and by actually drilling riblets on the top of the wing, you can reduce by 10%. It's huge, but it's still theoretical, but it's been demonstrated on R&D planes that you can reduce by 10% the consumption of the aircraft. Another very nice application is foil texturing of the batteries. I really hope that next year we're going to be working on that. Actually, one of the big challenges of the electric vehicle is to have at the same time a battery which is having a big capacity so that you can drive a lot of kilometers, but at the same time you want it to charge quickly, which is very difficult. And one way to have big batteries that you can charge quickly is to texture them using femtosecond lasers. So there are cool results on that, and it's going to actually scale up in the industry pretty soon. I guess I've been talking enough, and I will end the vote now and share the results with all of you. So now you should see your results on the screen. So we have had mostly people answering multiplied by 50. I'm quite happy you're answering 50 because we expect to do more than that within less than 6 months at Cailabs. So 50, I guess, is a good number still because what is important to know is that it's big. The scaling up needs to really be big. For now, we are talking in millimeter per minute, and we have to talk in meter per minute. If you want to texture the batteries, the manufacturing of the batteries is like super quick. And similarly, when you want to texture a whole aircraft, it's actually pretty big. So let's get back to the presentation. Okay, so all my next slides are all made similarly. So I will just explain how they're made so that you can easily read them in the next minutes of the conference. So you will have the application name on the box on the left, and everything which is related to the application, the material, the wavelengths, the different process parameters which we're actually using, and an image of the process sample. You always have an image of the process sample. What we do is we do beam shaping, and that's how we improve the process. So on the right are all the information which are related to the beam shaping. What type of shape, what different beam parameters were being used, and an image of the one shape in the processing plane that we have been using. And our target when we do this test is always to compare ourselves to something, compare to non-shade beam, compare to other technologies, and to demonstrate that we can improve things by a factor of something. So in the big circle, there is that one number that we are really looking for. Unfortunately, I will not name all our partners, but you have the logos of the partners also on each slide. And most of those results have been presented in one dedicated conference. Generally, it's Photonic West or actually LIM in Munich, where we have a lot of papers, and you have the reference paper, and I can actually later on send you the slides if you wish. So improving process speed. First result is by doing something pretty classical, which is beam splitting. So we divide the beam into 5 beams. Why 5? Well, the energy which was available on that laser was enabling processing 5 times faster theoretically, and not more, because there was not enough power, not enough energy. Actually, it's often the case. Splitting by 100 beams is not so useful for now for most applications, because you don't have enough energy in the end in the single beams. So in that case, we were actually drilling small holes on stainless steel, and the idea was to do surface texturing to improve the tribological properties. So we want to improve the process speed while maintaining the quality. That was the one big challenge that we demonstrated, and it worked. Why do we improve the process speed by only 2.5? This is due to the scanning strategy. So you have your 5 beams, you are actually drilling your holes, then you have to move the scanner and drill again 5 holes, and you move again the scanner. So basically, when you move the scanner, you lose a lot of time. In that case, half of the time, more or less. But if you think a bit further, it means also that the larger the area you are texturing, the closer to a multiplication by 5 of the process speed you will gain, because this time that you have to move the scanner is going to be proportionally lower and lower. So 2.5 times for 4 by 4 millimeter, that's the result that we have demonstrated. And now it's time for Eric's first question. Eric, what is your question on that one slide?
Well, my question was, how are you actually splitting the beam? Are you splitting the beam using your multiplane light convert, MPLC, or are you using something like a DOE, diffractive optical element?
Okay, thank you very much for that question, Eric. I believe actually many people have the same one question. So you will confirm that later on, but I did not force you to remove any of the question. Obviously, I know the question that he's going to be asking, but I did not force him to remove any question. If there were one question I would have removed, it would be that one. But Eric, you asked it, so I will have to answer. Yes, actually, there is some diffraction effect when we are doing that one results, which is splitting the beams into 5 Gaussian beams. So it's not pure MPLC technology. Nonetheless, it's not exactly a DOE either. We try for some specific break, some specific feature that we have to have. We are not using our historical MPLC way to do beam shaping with MPLC. And we use some diffraction effect, but nonetheless, we do it differently compared to the DOE. For example, we can remove the ellipticity. We can also remove the higher orders that you are using, that you are having when you are using a DOE. The technology is also fully reflective, which makes a huge difference because it's also globally in the way you are using it's actually pretty different. And I would say that our strength is not just splitting the beam, but adding a lot of functions. So in the end, most of the time, there is an MPLC, a pure MPLC somewhere. But in that one very case with Manutech, it was something which is more based on diffraction that we have been using. Have I answered your question, Eric?
Absolutely. Yes, thank you.
Okay, great. So let's continue with one cool result, which is a very old result, actually 2020, which was increasing the process speed using a line. So why using a line? Well, actually, if you have two big beams, you are somehow burning the surface. So you cannot make the beam just bigger and having more energy. It's not working. But there is something which is pretty smart. It's using, for surface texturing, which we were doing in that case, lift generation, it's to use something very specific of polygon scanner. So polygon scanner can go really super fast, but in one direction, and in the other direction, they are a bit slower. So what we did is having a line, which was actually parallel to the fast axis of the polygon scanner. And in that case, we were scanning super fast with that line, and then we translate it in a slower way somehow, but we go again super fast with the line. So that's actually a good way to optimally use the principle of a polygon scanner, and compared to a Gaussian beam, which would have had somehow a 30 micron size, which was the size which is optimal for that one process, we improved the process speed by a factor of 20. So Eric, you were also having a question on that one.
I did. So I was curious, what role does polarization play in the directionality of the generated lips?
Actually, it's a very good question, and in those cases, I make a quick answer because we are not process experts. We are optical experts in shaping the light and using all those setup optically. Nonetheless, definitely, it's very important to control the polarization. And generally, you have linear polarization, and when you rotate it, you have lips which are pretty different. And our main focus was to not change the polarization. So what we made sure is that the polarization after our system was still linear, because they were using linear polarization before our system. All good? I see you are saying yes, so let's carry on. That one is currently one of my favorite results because it's super promising. So in that case, we want to do surface texturing. The application is the riblet I was mentioning for aviation. So you want to drill something which is very square on the top of the wing. So you have to drill long square riblets. And if you want to do it with a Gaussian beam, if your square is that size, the only way to have something which is compliant in terms of quality is to have small Gaussian beam and slowly go through that gutter somehow with this small Gaussian beam. So you have to have a lot of lateral passes, 13 to be exact in our cases. What we demonstrated is by having a square top hat which is pretty sharp, of exactly the correct dimension, you can do that with one pass, one lateral pass. You don't have to have overlap, which is making a huge difference because you can also use more energy to do that. So by having just one pass instead of 13 and using more energy, we demonstrated actually that process speed can be increased by more than 10. Actually, if the exact number, if I'm not wrong, is 17. But anyway, more than 10 in that case. And this is not the limit. In that case, we were doing just one square. So comparing one Gaussian beam to one square. The next step, which will be implemented in Bordeaux in February, is having multiple squares, one next to the other. So the target is to have 9 squares. So we will go to around process speed improvement in between 100 to 200 compared to the initial process speed of that riblet generation. So stay tuned because definitely that's going to be a cool result that we will have to present in 2024 with amplitude on riblet generation. So Eric, what was your question on that one slide?
I had 2 questions on this one. So my first one was, are you using scanning for those 21 longitudinal passes? And then the second question was, what the channels that you're making are square edge. So if you rotate that, are you able to get a V groove?
Okay, so for the longitudinal pass, definitely we are using scanning, so we are just passing again, because if we want to do it just one pass, we will need more energy, and in the end there would be too many thermal effects, so it would damage the part. So yes, we still have to go 21 times in this one riblet. For now, at least, that's how we did that. The other point is actually very smart. We had a European project where we had to drill triangular grooves, which is coming very soon or so in the next slides. And the first idea of our team was exactly what you said, just rotate the square. If you rotate the square, basically you will have the maximum depth, which is in the very middle. So definitely it works. I would even say that one of the challenge is to not do that and to really scan perpendicular to the square, because you want it to be very square in that case. And another important point is it's not so complicated to rotate the shape, at least for microprocessing application. For macro processing application is a bit more tricky, but for this one, we have nice results of a system which was developed in collaboration with Laser using a Dove prism, and it's working fine. So rotating the square is possible, and it would actually give what you were saying. Okay, cool. We can continue. So Laser now, a good old partner of Cailabs. We work with them for 4 years now on different topics, improving the different process they are developing. So in that case, it was pretty original application, micro welding. So when we were doing that application, we were actually working on PCR microchips. And back then, we didn't know what was a PCR microchips because there was no COVID yet. Now we definitely understand what they are. All those small plates that they were manufacturing, everybody knows, unfortunately somehow. But it's pretty funny that we did work on that before. And the idea was actually to mainly to improve the quality. So we were having an optimally optimized profile, which is U-shape. U-shape meant that there is less energy in the middle and more energy on the edges of the shape. And this shape, this kind of U-shape, when you're scanning, is actually giving something homogeneous in terms of intensity seen by the process, by the part actually. So that's actually pretty good for the quality. And because the quality is improved, the thermal profile seen by the material is improved, we could also go faster. That was a good surprise. So we demonstrated that using the optimal shape can, in that case, improve the process speed by a factor of 9 with Laser for welding. One last one, unfortunately, in that one, half of it is confidential. Nonetheless, there are some stuff that we can say, and I find they are pretty important, because in that case, this is a super industrial application. We have to actually do surface treatment, cleaning of some part using a square topat. The idea is, again, to scan perfectly and to go super fast with a lot of energy and a lot of power of the laser. And every percent that you can gain in terms of efficiency of the process was super important for the customer. So what is efficiency? That one was the hard one. Efficiency of that one shape, topat shape, so basically something which is having that kind of profile, is removing everything which is useless. The hard part is everything which is above the ablation threshold is useless, because you could be at the threshold. Everything which is below the ablation threshold is also useless because you are not doing the process. So it's actually really the energy which is inside the one main parallelepipedic shape, which is useful defining the efficiency. And I can promise you that this project, they really wanted the DOE to work, because for some reason, economical mainly, that would have been maybe a good solution. But we demonstrated that the efficiency of what we were doing was actually way better compared to DOE, which were optimized and used optimally. So the efficiency of the DOE was 45%, so 45% of the energy at maximum was useful versus nearly 60% for us. And in addition of that, what was super important is that we can have this 60% efficiency with a depth of field which was 4 times higher, plus or minus 20 millimeter. And you can imagine actually that plus or minus 5 millimeter for an application, for an industrial application, is actually really less and really complicated. So this result is really somehow very important, because we can demonstrate that compared to a DOE, the process is more efficient, and it's also more forgiving, because the depth of field is 4 times higher. Okay, that's it for a process speed increase. So let's look at precision now of the processes. So I will again make you work a little bit. And we will go to the one next survey for you. Okay, so now you should see it on your screen and you can vote again. So this one is out of curiosity. What is the main challenge that should be looked at in terms of quality improvement? So finally, I see that probably we have had some mistake that there are two questions. It's single choice question. Anyway, sorry, it's a logistic issue. We will manage, but the question is split it in two. So there are different options: texture reduction, roughness reduction, diameter of the holes reduction, homogeneity increase, and transition zone reduction. So all those somehow are possible using beam shaping. The application are very different. The first one are more for drilling of holes. For example, for the watch industry, it's a good example. The other one are more for surface texturing. You want to texture, for example, a surface which will be water repellent for different reasons, and you want that it's really water repellent on one part and not on the other. So you need to have a very sharp transition in between the part where you have the texture, the part where you don't have. Another point, when you are doing texturing, for example, lips, it's important that it's very homogeneous over a large surface. And this is also not so easy, especially if you use something specific, which is DLEP, which is now super popular. It's surface texturing based on diffraction. So that's an interesting application. So that's some challenges that we are looking at. On the other side, there are also whatever is related to the quality of the hole, which is super important. So I will end the vote now and share the results. So you should see the results now. So as you can see, actually, I'm a bit surprised that the homogeneity increase for surface texturing is winning. It is actually super important for sure, and it is a change that we are looking at. I would say, as you can see in the next slides, everything is possible using beam shaping. So let's get back to the presentation now and the results. So I mentioned DLEP. This is our first results on DLEP. So basically, DLEP is based on making 1, 2, 3, 4 beams, not one for sure, sorry, but 2, 3, 4 beams interfering. So they have to meet on the part, and they generate interferences, which are generating multiple spots for texturing, for example. So in that case, what we did was somehow pretty simple. Instead of having Gaussian beam interfering, we have square top hat interfering, and it's making a huge difference. Because when you make Gaussian beams interfere, those 5 by 5, so 25 spots, are inside globally a Gaussian envelope. This is how interferences work. So it means that the spots in the corners will have way less energy compared to the spots in the center. So what we did is that the homogeneity in between all the 25 spots was really way improved using beam shaping. It was basically divided by 5, leading for sure to a very good contrast on the surface texturing that we were generating. So Rick, you can come back now. I guess you were also having some question on that one slide about DLEP. We can hear you now.
Yeah, sure. So I had two questions on this one as well. So as someone who is currently working on DLIP, I can definitely attest that the outer edges of those patterns are much less powerful, and so you have to overlay. So this is absolutely fascinating for me and quite exciting. So is the initial beam that you then split into this pattern, is the initial beam set as a top hat? Or are you, yeah. So is the initial beam set as a top hat, or is it the other way around?
Okay. You want to ask your second question, Star, or?
So the second question was, does a change to the period spacing of the DLIP, does that change the top hat pattern?
Okay, cool. Nice question. The simple way to do that is actually to shape first and then to split. That's how we do it. Because if you split first and then you shape, in that case, you would have to shape a lot of beams. and it's more complicated in terms of engineering somehow. And it's working very well to shape it and then split it. So we had a Gaussian beam at the input, then we shape it, then we split it, is the standard way. In that very one case, is we kind of did it simultaneously. I have to say that it was working fine. It was giving great results. The system was easy to use and very compact, but it was maybe lacking flexibility. So if we have to do it again, probably we would really do it in 2 steps, shaping and splitting, so that the splitting is more flexible. Because in that case, if we do everything together, it's fixed. So it was giving 25 beams, and that's it. And in the case that, because it's really bricks, which are one after the other, no, it will not change the shape of the beam if you change the pitch in between the different spots. So the pitch in between the spots when you are drawing DLEP is basically based on the angles that the beams are interfering, so they are meeting with some angle. So you can actually tune the angle, and it will actually tune the pitch, and it's not going to change so much the shape. So that was the point. So I guess it's more or less answering. We are starting on DLEP, so there is much more to do, and we are happy to actually further look at DLEP next year and probably do something again different and maybe more flexible. Okay, so next one. That one is actually super old results, 2019, glass drilling, but very interesting application, generating super small vessel beams using a reflective hexagon somehow. And what was really exciting in that project is that we managed to drill nanometer scale drills through glass. So the aspect ratio of those drills was 400:1, which is like huge. Definitely, you cannot get that with a Gaussian beam, but you can get that with a nice vessel beam. And our challenge was to get this very high aspect ratio vessel beam and to preserve the quality over that needle, which is a vessel beam. And you want to have something very smooth all along that needle to drill those nano channels. So we have repeated that on other applications with glass. I will not name all of them, but actually vessel beam of high quality are a pretty exciting topic in terms of beam shaping. Another result that I like very much is this application with triangle. So the idea is to drill metallic molds, which will be used to manufacture Fresnel lenses. So we all know more or less the shape of those Fresnel lenses. They have this triangular kind of pattern on the top of it. So we needed to have these triangular grooves on the mold. But those grooves are all different inside the mold, meaning that the maximum depth will be different and the position of the maximum depth along the groove will be different. So the smart way we found to do that is to use a triangle. So if you have a triangle and you are scanning perpendicular to one side of the triangle, you will actually have the maximum depth, which is in the very middle of the triangle. Then you rotate the triangle and you actually scan parallel to one of the side of the triangle. And in that case, the maximum energy is on that one side, and you will have the maximum depth on the edge of the groove. So by just tuning how you rotate the angle, which can be done super precisely, you can fine tuning where is your maximum depth of that grooves that you are drilling. So Eric, what was your question on that slide?
My question was about changing the beam shape during a process. Is it super complicated to make a change to the shape using MLPC? And if it's a simple thing, could you do it quickly? Could you make those changes between pulses?
So by changing the shape, you mean really changing like from square to triangle?
Yes.
Okay, it's an excellent question. Basically, using the MPLC it's made to be static in the beginning. So we are working a lot on increasing the flexibility. So we have demonstrated on high power application in a European project that we can do really dynamic beam shaping with multimode laser. With monomode laser, it's a bit more complicated. So we are working on live change of the size, which is not so complicated. We can also change the pitch when we are dividing the beams, but changing from triangle to round pulse to pulse, it depends on the frequency of your pulses, of course, but pulse to pulse, I would say it's complicated for now. So we can quickly change the shape, we can quickly rotate it, for example, but not pulse to pulse. That's too fast for us compared to the classical frequency of the lasers.
So you could rotate that triangle during the process if you wanted to come around a corner or something. You could actually make that rip. Oh, that's neat.
Yeah, that's cool. And actually, if you want to even think further, you can do that in 3D, meaning that we are now doing 3D shapes that we can rotate in 3D somehow for some processes during the process somehow. So I would say that big changes, like round to triangle, is difficult, but the rest is we can do stuff.
Okay, changing the orientation of that shape.
Yeah.
Okay.
Okay, so let's continue. Lips generation. What is cool with that result is it was our first result in green. So it took us time to look at lower wavelengths, with a high probability we will have results in UV to share next year. So it took us more or less 5 years from IR to green to UV, but everybody's the same issue, I guess, in the world. It's not easy to go to lower wavelengths. But we did it. So we have now very good, stable system in green, and we generated LEPs with a square top hat, and we managed to demonstrate that in between the area where you have your LEPs and the area where you don't have your LEPs, you can reduce the transition zone by a factor of 5 using this square top hat. So Eric, what was your question on that?
My question was about the overlap for those different sections. The image you're showing there is really fascinating to look at. When you have to overlap them, are there areas where there's going to be missing lips, or are you able to match up those lines very closely?
So actually, lips generation is super complex in terms of process, and I'm not an expert in that. Nonetheless, it's kind of magical. When you overlap, it's just increasing the lines. I don't exactly understand how, to some extent, and at some point of time, it's messing up everything. So when we do this kind of process, it takes quite a lot of time for our partners to optimize the number of passes. So they do 1 pass, 10 pass, 100 pass, 1000 pass. And at some point it's optimal and it's really nice, and then it's degrading again. So it's kind of complex for sure. And I definitely don't want to try to explain the physics behind that because it's super complex. So I carry on. Last big challenge, but not the smallest one, definitely, but the last one, fiber delivery. So I will again make everybody work a little bit. So let me again, share the last survey. Okay. This is out of curiosity again, giving your opinion. Everybody can have an opinion on that. What do you think will be the market share, the whole market processing increase when there will be really an industrial solution for fibering the laser? One more time, I don't have, for sure, I will not give you the answer because I guess no one is really having the answer. It's just having an opinion on that. Because I believe it's going to be pretty big, and we are heavily looking at that with different partners. There are solutions on the market, but nobody is really super happy with them for now. So it's something that a lot of people are working on, and hopefully also we will have more results to share within 6 months on that topic, having real industrial application using fibering, which will be based on multiple line conversion. So how we do that, actually, we use something very unique, which is called mode cleaning, to passively clean the mode and actually stabilize the beam. So it means that we have actually a pure MPLC, which is playing with the modes. So the principle of MPLC is that we propagate all the modes somehow one by one, and we play with them one by one. So when we see a beam which is, for example, elliptical or which is shifting, at Cailabs, we see that like some energy which is in the main TEM0, so Gaussian beam, and some energy which is in the higher orders. And the higher orders, we tell them, okay, you should go that way and being dumped somewhere. And we kept the good Gaussian mode going through the MPLC and going out of it. It means that the output of the MPLC is extremely stable and extremely Gaussian, which is extremely good for fibering. So I will go back to the result that we are having, and I will end the vote now and share the results with you. So you can see that people expect it to be big. I really hope it's going to be really big. Plus 100% is possible. It means doubling the market. There have been moments where microprocessing really doubled when more power was available. So for sure, fibering should open really new application to the world of microprocessing. When will it happen? It's a big question. I hope soon. We will see. So now my last slide on process result, which is good because it's already 10:45. Coupling into a hollow core fiber. I explained the principle already. Just want to now show the results. So we managed to demonstrate that the depointing was actually reduced quite a lot. I have a lot more data on that one. It's really providing a very stable Gaussian output. And the big thing is that it's increasing a lot the lifetime of the fiber. Why that? When the laser is warming up, it's moving quite a lot, which is okay. It's warming up. It's known. It's all the lasers are similar. The problem is that the active solution cannot follow up. So they will kind of mess up in the beginning, in the warm up, and the active solution regularly may actually kill the fiber in that warming up time of the laser. When you do it passively, what will happen is just you will have terrible transmission. If the beam is moving too much, the transmission is very low, and that's it. So it's not going to kill the fiber. It's not going to be wonderful. It's not going to work, but it's warming up time, so it's kind of okay. And actually, it's going to preserve the lifetime of the fiber. So, Eric, what is your last question on that one last slide?
Well, I once again, I had multiple questions on this topic. So my first question is, what was the max pulse energy that you've tried? And can you talk a little bit more about telling the other modes to go somewhere else? I'm fascinated by that idea.
Yeah, it's actually pretty cool. Huh? So first of all, 50 microjoule. Why? Because it's what they were having, and the fibers actually also are for now limited in terms of energy. But in principle, that one system which they were using is handling 100 microjoule, and it's not our limit. It's just the limit of the off-the-shelf version that you can actually purchase easily from our business team. But we are not limited to that. As I said, we already demonstrated systems up to 500 microjoule in femtosecond. It's just that it's for now custom development. So I would say the limit should not be somehow so much on our system, but more on the rest of the environment, which is maybe not capable of handling so much more than 100 microjoule. Then how we do this mod cleaning, it's really intrinsic of the technology. So we really, the principle is really to play with the modes. Initially on telecommunication, for example, when you were having 10 channels, each of them really carrying different data, we were saying, okay, this one will be mode 1, this one will be mode 2, this one will be mode 3. We put all of them inside the fiber and we divide them again so that we can have 10 times more data, for example, which is transmitted. It's the same principle. So we will have energy which is based on mode. The higher order modes, for example, the second mode is 2 lobes, so that will be used. That's energy which is from electricity. So if your beam is getting more elliptical, there will be more energy in that second mode, which is with the 2 modes. And if you one day have the chance to see an open MPSC, actually for now, how it's made, you have the Gaussian beam which is somewhere, and around it you will have all the other modes that we are actually directing around it. Then we kind of manage them, dump them properly, and manage the energy and the power which has to be dumped properly. I would say that there are many ways to organize them. We found one way which was working fine, but there would be other ways. And one important point is how many modes. The more modes you are using, which means that your input bin, you will divide it into a lot of different modes, the better somehow the cleaning will be. But the more complex the system is, and the more complex it is to align, and the lower the transmission. So there is a trade-off to be found. So we found a trade-off with a certain amount of modes, which I will not give online, but I can give it to you later on. But we could choose other configuration as well, and we could monitor that energy which is being dumped. If you monitor the energy which is being dumped, you know what is the energy which is going through, and you could actually have a feedback loop to the power of the laser to have a constant transmission, even if the laser is moving somehow. All good, Eric?
Fascinating. Thank you so much for letting me be a part of this and ask all these questions.
So this time you didn't take so many notes, but hopefully you could ask your question. So my takeaway messages, we are reaching the end of the webinar, but don't worry, we will find some time for the Q&A session. I generally conclude by saying it's terrible to sum up in 1 minute work that took maybe weeks or months to our partners. So thank you to all of them for everything they did. We don't have application lab. We don't plan to have an application lab. So we rely on experts to help us figuring out what we can do in terms of process with our beam shapers. Think out of the box. It's a big message. There are a lot of possibilities. This is just some examples, but I can tell you that our technical team is having a lot of crazy ideas additionally. So come to us, bring us your challenges, and we can figure out what is the best way to tackle those challenges. And I think I demonstrated it. It's definitely possible to address microprocessing challenges using beam shaping, all of them somehow. There are many strategies, so we have to figure out with you what is the best strategy for your own application. And I guess that we are hiring. I have to say that all the time. We are hiring, and we are reaching the end of the webinar. But we will now do the Q&A session before letting you go back to your work. So let's go to the Q&A mode. So the question list. Hopefully, it's going to work normally. And I will start by publishing some of the questions. So, of course, I didn't read the question before, so I hope they will not overlap with Eric's question. So how could I make multiple Bessel beam with your Easy Bessel product? Multi-Bessel beam with the Easy Bessel product, Easy Bessel might not be the best option to do multiple Bessel beam. I would say that definitely it's possible to do multi-Bessel beams, but probably we would have to use a different strategy to do that. It is definitely possible, but if you have the Bessel beam, which is already done, and you try to then split it, you might just actually kill your optics, because Bessel beams are really super intense and it's not so convenient. And yeah, it's not the best way to do it. So you have to do something more complex. And actually, in that case, you would have to do all together, splitting and doing the Bessel beams inside one MPFC cavity somehow. So very good question, very crazy idea. I love crazy ideas. Definition of the sharpness, excellent question. Well, the definition you want. What is super important that I really like to say now in conference is just to compare apple to apple and carrot to carrot. So whatever your definition is, at least it's important to know how you define it. What we do at Cailabs is we define the transition length from 90% to 10%. And this is a ratio to that transition length to the plateau length, which is the area where you have 90% of the maximum energy constantly over the plateau. So that's a definition, but we are open to any other definition. But when you want to compare DOE with MPFC, for example, it's important to use the same definition. And what is even more important is to use the same setup, because the numerical aperture of all your optics will definitely limit your sharpness. And again, doing something which is super sharp, but which is not limited by any scanner and any f theta, and which is very big, is actually super easy. What is challenging is to have a small beam which is very sharp and which is going through your scanner. So apple to apple, sharpness is actually a big topic, and the important is to really know what you are talking about. I'm very frustrated because I see it's already 10:44 and I cannot go after 11. So we will probably not be able to answer all the questions, but don't hesitate to reach us by email because I don't know how many we will answer, but probably not all of them. So what is the pulse application, the pulse duration for this application? Unfortunately, I don't know to what application it's linked, but I would say that our off-the-shelf products are compatible with 100 microjoule pulses for IR, 50 microjoule for green, and it's definitely not the limit. We have a custom systems which are handling much more than that. So let me try to publish the next one. first direction for aerodynamic performance improvement. It was a Tungor laser, so it should be 500 femtosecond. Tungor laser from amplitude. So how I can get M-shaped beam? Technically, I mean, well, using a monopore system, the M-shape is for now not off the shelf, but not very complicated to make. So definitely reach us. We can develop a system for you to have this M-shape. So what is the target? The largest amount of spots you can have. Basically, there is no limit. If it's just a number of spots, what is the limit is your setup will limit the number of spots, because again, you have to go through the scanners and all that. So that's a limit. Then there is a limit in terms of spot size versus pitch in between the beams. There is a limit against regarding the homogeneity. So if you want to have a super high homogeneity, a very big pitch compared to the spot size, and go through a small scanner, it's impossible. So there are limits, and I think the good way to see that is to come up with what you want, and we'll make all the calculation and see if it's possible. If it's not, we will propose some alternative. Do you sustain flat wavefront for flat top converters after you dephase? Exactly. Thank you so much for the question. That's exactly what we are doing, and that's how we manage to have a very good depth of field. Why the M-shape is better? What is the physics limit behind that? The M-shape is better because when you have a round, which is a top hat, and you are scanning, you have more energy in the middle compared to the edge. And there is an optimal profile, and you can calculate that. And when you are scanning, the intensity which is seen by the material is optimal. It depends on a lot of different parameters like scanning speed, overlap, beam size, and all that. But it's not so complicated. It's been actually demonstrated on hardening for more than 10 years, I think, because for hardening, they also do kind of flat top with multimode laser. And they also demonstrated that it's best to have something which is not perfectly flat, to have a homogeneous thermal profile seen by the material. So actually, the M-shape is useful for microprocessing. It's also useful for macroprocessing, and hopefully we will use that for hardening and for LPBF in 2024. Does the side lobes of the beam interfere with the results? It's a good question. That's actually always a challenge, the side lobes. So the result I was showing today were with normal side lobes. We didn't do anything for that. But there are ways to remove those side lobes, or at least to reduce them quite a lot. So if you have some interest in that, reach us. It's super interesting. It's possible to play on that. What is the efficiency of your flat top shapers? Well, it depends. It's not so easy to say. It depends a lot on the numerical aperture, the size of the beam, and all that will give you a sharpness. So if the flat top is very sharp, the efficiency will be better. And if the flat top is smoother, there will be less energy lost in the edges. And again, we can reach what your setup enable, but there are limits based on your setup, based on your scanner, and we cannot break the limits of physics. It's still not possible. So actually, I guess we are actually good. We have been through most of the questions. Perfect. 2 more minutes just to say goodbye. So enough time to go back to the camera. And thank you, Eric, so much for being our guest today, for waking up at 3 a.m.
I didn't mind at all. I was going to join this webinar whether or not I was here helping you, getting to ask you questions. So it was great for me.
Okay, I was really happy having you. Hopefully we will see each other very soon in other conferences. And I'm happy that in the end, I hope you got your answers of all the questions you were having.
I did. I was also fascinated by one of the last questions that I didn't know this. You sustain your flat wavefront after your so it's not just a flat top at focus, but it actually sustains it. I actually didn't know that you could do that. So that's a big deal for me as well. So I'm quite excited about that idea.
Okay, then don't hesitate to reach the sales team, Eric. Okay, thank you everyone for your time. Thank you for being there. I think we were pretty happy. There were many people connected. I wish all of you Merry Christmas and a Happy New Year. See you next year, somehow online or in conferences. And have all of you a good end of year. And again, thank you, Eric. See you soon.
Thank you, Gwen. Excellent presentation. Merry Christmas.
Bye bye.